Welcome to the deep dive, where we crack open the technology that underpins the modern world.
Yep.
Today, we're focusing on some of the most, well, silent and indispensable workhorses of electrical control. We're talking about relays and contactors.
Right. And these devices are the fundamental building blocks of automation. You see them everywhere, whether it's, heating systems in a high-rise, conveyor belts in a factory.
Or even the control panel for large-scale lighting. They're everywhere.
They really are the traffic cops of electricity. They take a tiny, low-power signal and use it to safely direct a much, much larger current.
So our mission for you today is, I think, pretty clear.
Yeah, we want you to leave this deep dive able to look at any relay or contactor nameplate and just get it.
You'll understand its critical requirements, you'll know the internal physics that keep it from destroying itself, and you'll grasp that vital difference between its coil and its contact rating.
Exactly. We're going to distill what separates a relay from a contactor, explore those ingenious design tricks that stop the AC components from humming themselves into scrap metal.
And decode the critical voltage thresholds, the secret language of the electromagnetic switch.
So let's start right there with that foundational distinction. Because, they look so similar structurally.
They really do. Both are electromagnetic switches. But the distinction is, well, it's crucial for picking the right one.
It is.
At its heart, a relay is all about control. It's about information processing. It's an electromagnetic switch that controls a load, usually a pretty small one, based on a signal it gets from an information source.
Like a sensor, a PLC output, or just a simple push button. It's the go-between.
It's the intermediary, exactly.
Yeah.
So what about the contactor?
Well, we say that term for the devices doing the heavy lifting.
Okay.
They're built like relays, but they're designed to handle significantly higher current loads.
So we're talking big, high current, non-motor loads or controlling motors.
Right. But with the caveat that the motor's overload protection is handled by a separate component.
Okay, so I can think of it as a matter of scale. A relay is for low power signals and sequencing, and a contactor is for when you need to switch some serious current, like, I don't know, turning on a 100 horsepower motor.
That's the perfect mental shorthand. And whether you're dealing with a tiny little plug-in relay or a massive industrial contactor, they all rely on the same internal magnetic system.
The core mechanism is universal. You've got the coil,
Which is the winding of wire. You put electricity through it, you get a magnetic field.
and that field magnetizes the stationary metal part, which we call the core.
That's your electromagnet right there.
And then finally, the armature.
The armature. This is the movable piece of metal that sits near the core.
And when that core magnetizes, it just yanks the armature towards it.
Exactly. And that physical movement is what gives you the mechanical force to change the state of the electrical contacts.
So the cycle is super simple. Energize the coil.
The core magnetizes.
The armature gets attracted.
And the electrical contacts shift. You're normally open, or NO, contacts will close. You're normally closed. NC, contacts will open. That movement is control.
So if the parts are all the same, why is there this just incredible variety out in the field?
The application.
Yeah.
It all comes down to what you're using it for. That dictates durability, mounting, everything.
Okay, so let's start simple. Let's say I'm just switching a small heater or a fractional horsepower motor.
For that, you'd use a power relay. They're often open type. You can see the contacts, and they're rated up to about 30 amps.
And they're mechanically simple, but what's the catch?
The catch is they are not designed for fast or frequent cycling. They're built to turn on and stay on for a while. Long, steady holds.
Got it. Then you have what I see everywhere in control cabinets, the plug-in relays.
The ubiquitous plug-in, yeah.
Oh.
They're enclosed, rated up to maybe 15 amps, and they connect with these little tubular or spade pins into a terminal base.
And the big win there is maintenance time, right?
Oh, absolutely. Being able to swap a faulty relay in 30 seconds without touching a single wire is just invaluable in a complex system.
And for anyone troubleshooting, there's a key detail to remember.
That for every NONC contact set on a plug-in relay, you need 3 pins. One common, one NO, and one NC.
Moving up the food chain, we get to the industrial control relays.
Now, these are built for heavy-duty cycles. They're designed for extreme longevity,
Yeah.
and they're highly modular.
And modularity is key for system designers.
It is. It means you can often replace individual bits, like the contact cartridges, or you can add more contacts using these adder decks that just stack on top.
So you can customize it on the fly without ripping out the whole unit.
Exactly.
We should also touch on specialized stuff like low voltage lighting relays.
Oh, yeah, latching relays. You hit a coil for a split second to close the contact, and then you hit a second coil to open it,
No constant power draw.
which is great. And a quick note on terminology for our Canadian listeners. The industry calls them low voltage, but under the Canadian electrical code, the CE code, they're actually extra low voltage if they're below 30 volts AC or 60 volts DC.
That's a crucial distinction for installation rules.
It is.
Okay, so let's talk about the big guys. The full-size contactors. Here we run straight into this philosophical divide.
NEMA versus IEC.
And it's not just two standards, it's two completely different ways of engineering a product.
That's right. NEMA, the National Electrical Manufacturers Association, they emphasize robustness, simplicity, general purpose duty.
So a NEMA size 1 contactor can handle a huge range of jobs within its rating.
They're simpler to select, and they are incredibly rugged, built like tanks.
But the trade-off for that is size. They're bulky.
They are. If you're building a panel where space is tight, NEMA might be overkill.
Which is where IEC comes in.
The International Electrical Commission. They focus on designing for the intended life cycle of the specific job.
So they're more precise.
Much more. They run a bit hotter internally, and the design is tailored to the exact duty required. So the contactors end up being significantly smaller than their NEMA equivalent.
So on the shop floor, it comes down to panel space and how specific your application is.
Pretty much. IEC saves space, but you have to be more careful with your selection. NEMA is massive, durable, and easier to keep as a spare.
And just like with relays, we see specialization within contactors, like reversing contactors.
Right, for any motor that needs to run in both directions.
And that's a really clever assembly. It's just two regular contactors that are linked together.
They're interlocked, mechanically and electrically, to absolutely guarantee that both can never close at the same time.
Because if they did...
You'd have a massive phase-to-phase short circuit, a big bang.
Not good.
Not good. And my personal favorite for noise reduction is the mechanically held or a latching contactor.
These use two coils, right? One to close it, one to open it.
Exactly. The beauty of it is once the contacts are closed, a little mechanical latch holds them. No more power is needed for the coil.
Which eliminates two huge problems. One is the constant power draw from a normal coil.
And the other is that low, persistent hum. That 60-cycle hum can be really objectionable in places like hospitals or, quiet office buildings.
Okay, so let's move to the nameplate. This is the most crucial part for selection and troubleshooting.
It is. And you have to be able to instantly tell the difference between two sets of numbers on that plate.
We're talking coil ratings versus contact ratings.
This is the source of so much confusion for new people. The coil rating is the voltage the electromagnet needs. That's your control circuit voltage.
Right, and that might be something small, like 24 volts AC or DC.
But the contact ratings, the current, the voltage, the horsepower, they're completely separate. They relate to the load circuit, which could be 600 volts AC three-phase.
So you have to check both. The control voltage has to match your control circuit, and the contact capacity has to be bigger than your load.
Always.
Okay, let's decode the contact language, the form system.
It's a shorthand manufacturers use. Form A is your simplest setup, single pole, single throw, normally open.
A basic on-off switch, a gate.
Yep. Then Form C, that's the workhorse of relays, single pole, double throw.
So you've got one common terminal that switches back and forth between a normally open terminal and a normally closed one.
Right, and then you get the specialized ones, Forms X and Y.
Form X is a single pole, single throw, normally open, double make, often called a bridge contact.
And Form Y is just the normally closed version of that. Single pole, single throw, normally closed, double break.
What's the engineering advantage of that double make or double break?
It's all about lifespan. Instead of the current arcing across one single point when the circuit breaks.
It breaks at 2 points simultaneously.
Exactly. The bridge contact opens in two places. It doubles the air gap, splits the arc voltage, and helps extinguish that electrical arc much, much faster. It dramatically increases the life of the contacts.
That idea of a long life brings us to the physics inside these AC devices. I mean, if the magnetic field on an AC coil drops to 0 120 times every second.
Why doesn't the armature just violently chatter itself to death?
Yeah. What kind of engineering trick stops that destructive vibration and all the heat it must generate?
You've just hit on the two biggest problems with AC controls. Heat and chatter. The heat comes from something called eddy currents.
Okay.
When you run AC through the coil, it induces a voltage in the core and the armature themselves. That induced voltage creates these little internal circulating currents,
The eddy currents.
and they generate a lot of heat and just waste magnetic efficiency.
So the solution to the heat is, well, it's simple engineering brilliance. Laminations.
Absolutely. The core and armature aren't made from a solid block of steel. They're built from many, many thin sheets or laminations that are insulated from each other.
And by doing that, you increase the resistance across the path those eddy currents want to take.
And you just choke them off. You drastically reduce their size and cut down on all that wasted heat.
Okay, that deals with the heat. But the vibration, that notorious hum and chatter, is still a threat.
It is. Like you said, the AC sine waves passes through zero, the magnetic flux collapses, and the armature springs back open, even for just a millisecond.
And that rapid opening and closing is chatter.
It's deadly for contacts. It causes intense arcing, which leads to pitting, oxide formation, and eventually high resistance and failure. The fix for this is the truly elegant shading coil.
This is where it gets really cool. That little single copper loop embedded in the face of the core, what is it actually doing?
It's an induced phase shifter. The main coil's magnetic field induces a current in that copper loop.
Okay.
And that induced current creates its own separate magnetic flux that is deliberately out of phase with the main coil's flux.
Ah, so when the main magnetic field drops to zero,
The shading coil's field is still strong.
it's still pulling.
It's still pulling. It's a perfectly timed secondary magnetic pole that acts like a bridge across those zero crossings. It makes sure the armature is always being pulled tight against the core, and that eliminates the chatter. It is vital for AC control longevity.
Speaking of longevity, let's talk about the contact materials themselves, the bits that actually switch the current. There's a serious trade-off here.
A huge one. We mainly deal with three types of material. First is silver.
Great conductor.
Fantastic conductor, and it's often called self-cleaning because silver oxide is still conductive. That makes it amazing for low-level signals where you need total reliability.
But the drawback.
It's soft. Silver will easily weld itself together under high current, which is a catastrophic failure.
So for high current, you move to copper.
Right. Copper is much harder. It can handle higher current and voltage.
Yeah.
But copper is prone to some nasty pitting and oxidation. If it's cycling frequently under load, it's not great for stuff that's switching on and off all the time.
Which brings us to cadmium.
Cadmium gives you the durability you need for constant strong spring tension and frequent switching under load.
Its conductivity isn't quite as good as silver, though.
No, but its hardness and resistance to wear is what makes it ideal for industrial use. That's why you see alloys like silver cadmium oxide so often. You get the best of both worlds, resists welding and pitting.
Durability isn't just about the material, it's also about the mechanical design. When contacts close, they slam together, and this causes secondary arcing from contact bounce.
And that's all managed by spring design. You have contact springs that are engineered to absorb that initial impact and minimize the bounce.
And then you have armature springs?
Those are designed to do the opposite, to quickly snap the armature back to its normal position when the coil de-energizes, often working against gravity.
And as we mentioned earlier, the physical shape of the contacts, like those bridge contacts and bifurcated contacts, also fight wear.
Bifurcated contacts, you see them in sensitive relays. They give you multiple parallel contact points, sometimes 4 per set 2, massively improve reliability, especially with really low signals.
All this mechanical cleverness exists just to support the electrical field. Which brings us to the operational thresholds, the final set of numbers you absolutely need to know.
Right.
We're talking about the famous 85% rule, the voltage you need to pull in the armature and seal it against the core. That's the seal-in voltage.
And that minimum voltage is approximately 85% of the coil's rated voltage. If you're below that, it either won't start or it'll start very, very badly.
On the other side, you have the dropout voltage. That's the point where the field gets too weak to hold the armature in.
And that's usually much lower, around 50% of the rated coil voltage.
Notice that gap. Seal-in is always much higher than dropout.
But let's talk about the physics that makes applying slightly too low a voltage so dangerous. Why is the coil current so much higher, like 4 to 10 times higher before it seals in?
It all has to do with the magnetic circuit being incomplete. Before that armature closes, there's a big air gap.
Right.
And that air gap significantly reduces the coil's inductance.
Then the armature finally closes, the air gap vanishes, and that causes the inductance to increase dramatically.
And since the coil's total opposition to AC current, its impedance, is so dependent on inductance, the impedance shoots up.
forcing the current to drop suddenly and stabilize at its normal low running level.
So if your voltage is a little below that 85% threshold, or if the armature is just physically jammed, that air gap never closes.
And the coil just keeps drawing that massive high initial current because the impedance stays low.
And that high current, drawn continuously, is what just cooks the coil windings. They overheat and burn out. It's a classic troubleshooting find.
On the high side, you never want to exceed 110% of the rated voltage.
Too much voltage can break down the insulation or just violently snap the armature into the core and damage the contacts. It's a really tight, precise window you have to operate in.
And one last thing. If you switch off the power and the armature fails to drop out, you're looking at one of three things.
Residual magnetism in the steel is holding it. The contacts have physically welded themselves together.
Or the armature is just mechanically jammed. That's your checklist.
So that gives you a complete operational picture. We covered the foundational difference relay for control, contactor for power, the need for laminations to kill eddy currents, the genius of shading coils to stop that destructive AC chatter.
The form system for contact configurations, and that critical importance of understanding the 85% seal-in voltage rule.
Mastering these seemingly small components is really the key to mastering large, complex control systems and getting good at troubleshooting.
You now understand the intense internal physics, that little battle being fought against heat, noise, and arcing inside every single control panel you open.
So what does all this mean for you in practice? I want you to think about the complexity embedded in every automated system you see. The difference between that high seal-in voltage, the 85% needed to pull it in, and the much lower 50% dropout voltage tells a story. It's about inertia and safety. That significant 35-point roofer is the extra magnetic muscle required just to get the process started reliably. What does that gap tell you about the safety margins engineered into every component you trust on the job? Think about the effort needed to overcome that initial resistance versus the minimal power needed just to keep it going. That tiny physics lesson is happening thousands of times a day in your facility.